I'm going to go through some of the questions from the Review 2 of the Polynomials unit, since we won't get a chance to go over all of them in class. Number 1, use the remainder theorem to determine the remainder of the following ratios. Well, remember, the remainder theorem states that if I'm taking a polynomial and dividing it by x plus or minus some number, that I can set that denominator equal to 0, solve whatever that is, and plug that number into my polynomial, and whatever I get represents the remainder. So that's what the remainder theorem states, but in practice, here's what it would look like for A. I'm dividing by x plus 1. So what I'm going to plug into the numerator of that polynomial is x equals negative 1. Now I get that just from looking at that denominator x plus 1 and setting it equal to 0. You don't always need to show that work if you could solve that in your head, but that's how I get that negative 1 there. Then, everywhere I see an x in the numerator, I would substitute in negative 1. So it would look something like this. Now, I don't expect you to simplify that in your head. You would just type all of that into your calculator exactly how you have it written with parentheses and everything. And when I did that, I got negative 5. So what that means is that if we were to do this division, we would get some quotient minus a remainder of 5 over x plus 1 if we were to do the division. Or in other words, this very much shows us that x plus 1 is not a factor of the numerator because it doesn't go in evenly. I would need a remainder of 0 for that to be the case. So a lot of the times the remainder theorem can speed up our work. For something like number 2 especially, if the ratio of x squared minus 11x plus 22 divided by x minus 9 was placed in the form q of x plus r over x minus 9, so that's just saying your quotient plus your remainder over your divisor, then which of the following is equal to r? Well, if I see x minus 9, I can plug in x equals positive 9 to the numerator there. So 9 squared minus 11 times 9 plus 22. Again, I would just type all of that into my calculator, and it tells me 4. So if I were to do the division, the remainder would be 4. Another way we could phrase that question is something like number 3. Consider the polynomial function p of x equals 2x cubed plus 3x squared minus 2x minus 3. Evaluate p of negative 1. So again, that just means everywhere I see an x, I would substitute in negative 1 and evaluate. So I worked all these out beforehand. Now I already evaluated this and typed it into my calculator, but when you do all this, you should get 0 out. So when I did all this, I evaluated, I already typed it into my calculator and I got 0. And the second question says, based upon your answer from part A, can you determine one of the factors of p of x? If so, what is the factor? Well, remember the remainder theorem. If I'm plugging in negative 1 into my function, that means I'm seeing what the remainder of p of x divided by x plus 1 would be. So if my remainder is 0, then I could say, since p of negative 1 equals 0, x plus 1 is a factor of p of x. So that's because that 0 represents the remainder, and I got the x plus 1 just really by taking the opposite sign of that. The last way you can consider a remainder theorem question is something like 4. If x minus 3 is a factor of x cubed plus kx squared minus 11x minus 3, then determine the value of k. Well, there's a really important piece of information here. They tell us that x minus 3 is a factor of that polynomial, which means if I take that polynomial and plug in positive 3, I should get out a remainder of 0. So this is an important relationship that can help me solve for a value of k there. So I can substitute in 3 everywhere I see an x. And because I know x minus 3 is a factor, when I substitute in positive 3, it all should evaluate to 0. So now I have an equation with just one unknown that I could simplify a little bit to solve for k. So 3 cubed is 27, 3 squared is 9, 3 times 11 is 33, and then notice I've got a bunch of constants that I combined there, 27, negative 33, and minus 3. If I add all those together, I would just get a negative 9. And if I solve this equation for k, I could add 9 on both sides to get 9 equals 9k, and divide out the 9 on both sides to get k equals 1. I also want to show a couple of examples of how we could use reverse tabular to divide polynomials. The first thing you want to make sure of is that when you're dividing polynomials, that all of your polynomials are in standard form. What that means is that all of your exponents of x are accounted for. So notice in my numerator I've got an x cubed, an x squared, an x to the first, and technically an x to the 0. So that checks out. And that they count down in that order, starting at the biggest and going down to the smallest. So originally this polynomial wasn't in standard form, so I just rewrote it. And I want to divide that by x plus 2. So what I'm going to do there is I'm going to set up my boxes. I know I'm going to have 2 rows because I'm dividing by x plus 2. So that's a linear term and a constant, 2 different things. To figure out how many vertical pieces to draw, I could subtract the degree of my numerator and the degree of my denominator. So the highest power of x I see in the numerator is 3, and the highest power of x I see in the denominator is 1. So if I subtract those, I get 2. That's how many vertical pieces I want to draw in there. And that will ensure that you have enough room along your diagonals to fill in every term of your numerator. So I'm going to put my 3x cubed there. That's 3x to the third, right? And then my 12x squared goes next because that's my degree 2 term. Then 11x, that's my degree 1, and negative 2. And the process always starts the same, whether there's a remainder or not. I start with that top left-hand box, I put that in, and I ask myself, what would I have to multiply x by to get 3x cubed? And that's what's going to go above 3x cubed. Well, I know there would need to be a 3, and if I take x and multiply it by x squared, I get x to the power of 3. Once I have that filled in at the top, I have a 3x squared there and a 2. I can multiply them to get what goes in that bottom left-hand box there. So 3x squared times 2 would be 6x squared. Now, the next part of this is I can look at this diagonal. That's where all of my x squared terms are going to be. Altogether, I want them to sum to 12x squared, but I already have 6x squared accounted for. So to make them sum to 12, I would need another 6x squared there. Then, I can ask myself a similar question as before. What would I multiply x by to get 6x squared? Well, I know I would need a 6x, because 6 times the coefficient of 1 there would be 6, and x times x is x squared. Now that I know what's on top there, I can multiply the 6x by the 2 to get what goes in that box right down there. So 6x times 2 is 12x. Again, I look at my diagonal now. I want the whole thing to add up to 11x, but I've already got 12x's accounted for, so I've got one too many. So I would need to have a negative 1x there, or just negative x, so that 12x plus negative 1x is 11x. Then I ask myself, what do I multiply x by to get negative 1x? That would just have to be negative 1. Oops. Let me just make that in black right there. So this part in the top, that 3x squared plus 6x minus 1, that's going to be the quotient, or the answer to the division problem here. I just need to check to see if there's a remainder. So I can multiply the negative 1 times the 2 and put that in the bottom right-hand box. That's negative 2. And that's exactly what I wanted to get there because that's the constant I started with. So there is no remainder in this case. And your final answer can be 3x squared plus 6x minus 1. That's what you would get when you divide the numerator by the denominator there. That's an example where there is no remainder. Let's try an example where there might be a remainder. Number 7. Determine the quotient and remainder when 3x to the fourth minus 21x squared plus 54x plus 5 is divided by 3x squared plus 6x minus 18. So a few more terms to worry about here, but one of the things I notice is that in this polynomial, it's missing an x cubed term. So make sure to include a placeholder when you're setting up your boxes for division. Well, I'm dividing by this x squared term, so I'm going to set up my boxes. There's going to be 3 rows because I'm dividing by 3x squared, 6x, and minus 18. The question is how many vertical slices to draw. Well, if I'm dividing a degree 4 by a degree 2, I can draw 2 vertical slices if I subtract those degrees. And you'll know if you did this correctly because you'll have enough room for all of the terms of your dividend, or the thing you are dividing by. So 3x to the fourth on your first diagonal. The second diagonal would be 0x cubed. Make sure to have that placeholder so all of your terms are accounted for. The big diagonal with those 3 terms in those boxes would be negative 21x squared. Your second to last one is 54x, and the last one is plus 5. Now it's really easy to make a mistake going through this in terms of just adding numbers wrong or forgetting a negative somewhere, so make sure you're being really careful. Generally, your numbers shouldn't be too big that they're overwhelming to work with. But let's start this the same way. I'm going to put that 3x to the fourth in the top left box there, and I'll ask myself, the same question as before. What would I multiply 3x squared by to get 3x to the fourth? Well, the 3 is already there, and I know that x squared times x squared would be x to the fourth. Now that I know what goes up there, I can fill in the rest of this column here just by multiplying. So I can multiply x squared by 6x to get what goes below that. So 6x times x squared would be 6x to the third, and x squared times negative 18 would be negative 18x squared. So now I'm going to deal with my diagonal for my x cubed terms. I want this entire diagonal to add to 0x cubed, and I have 6x cubed accounted for already. So I would have to add negative 6x cubed to that to make it sum to 0. Now that I have that, I ask myself again, what would I multiply 3x squared by to get a negative 6x cubed? Well, I know there'd have to be a negative 2 there to get the negative 6. And if I multiply x squared by x, I'd get x to the third power. Now I can fill in the rest of this column by multiplying. Negative 2x times 6x would just be negative 12x squared, right down there. I'll put that in purple. And negative 2x times negative 18, remember a negative times a negative is a positive, so that'd be 36x right there. Now I'll work with my x squared terms. That's a little bit of a bigger diagonal. Altogether, I want this diagonal to add to negative 21x squared. So let's see. I'm going to do a little bit of work off to the side here. Currently, altogether, I have negative 30x squared. And I want that to add to negative 21. So if I take those coefficients, and you might already see what it has to be, and subtract them, negative 21 minus negative 30, that would just be adding 30, and that would be 9. So I would need a 9x squared there. Now again, I'll ask myself, what do I multiply 3x squared by to get 9x squared? Well, I would just need a 3, because the x squared's already there. Then I can continue to multiply. 3 times 6x would be 18x, which checks out because 36x plus 18x along that diagonal is 54x. But 3 times negative 18 would be negative 54, which is a little bit of a problem, but we could fix it. Because that's not what I wanted to get there. I wanted to get the 5, but I got the negative 54. So to find your remainder, you could take what you want minus what you got. That's how much more you would have to add to that box to make it equal 5. So I would need positive 59 more, so that's going to be considered my remainder. So to write my final answer, I'm going to take this quotient on the top, x squared minus 2x plus 3, and add to it the remainder over the divisor, the 3x squared plus 6x minus 18. That's what I divided by, and that's how I would express my final answer. And this is like the worst case scenario where you need to remember a placeholder and you're dividing by 3 terms instead of 2. So if you can handle this example, this is as bad as reverse tabular can ever get. And just to go through the last example, number 8. This is another reverse tabular. So I'll set up my boxes. I'm dividing by 2 things instead of 3, so it's a little bit more manageable. And I'm dividing a degree 3 by a degree 1, so there should be 2 vertical slices I draw here. One there, and try to make them as even as possible. Mine aren't always perfect, but the more organized you can be, the easier this process is going to be. So I start with a 6x cubed, 17x squared, 10x, and then I hope for that last number to be 2, but I bet there's going to be a remainder based off of what these answer choices look like. Now, I'll start the same way. 6x cubed. I ask myself, what do I multiply 2x by to get to 6x cubed? Well, 2 times 3 would get me 6, and x times x squared would get me x cubed. Now, 3x squared times 3 would be 9x squared. But I want that diagonal to add up to 17. So I think about that, well, I've already got 9. If I added 8 to that, that would add up to 17. Again, if you're not sure, you could always just do a subtraction problem off to the side, and that'll get you that coefficient. Now I ask myself, what do I multiply 2x by to get 8x squared? Well, 2 times 4 is 8, and x times x is x squared. Now 4x times 3 is 12x, and I want this diagonal to add up to 10x, so I would have to take 2 away from 12. Now what do I multiply 2x by to get negative 2x? I would just need a negative 1, and negative 1 times 3 is negative 3, so I'm pretty close here. Just by looking at it, I know it has to be answer choice 1 based off of what that quotient is, but to get the remainder, I could take what I want minus what I got. So my final answer would be 3x squared plus 4x minus 1 plus my remainder over my divisor.